So as you know, here at CERN, we are always following cutting-edge technologies, in particular in our IT department. As it says in this event, quantum computing is an exciting emergent field at the interface of computer science, engineering, mathematics, physics, and it has a rapid development in these recent years. Therefore, the academic training wanted to coordinate and join the new quantum computing initiative effort to introduce this quantum computing with different algorithms and potential high energy physics applications with the hand of Heather Gray, our great speaker for today and the next 2 days. But before introducing her, I would like to give the floor to Alberto Di Meglio, who is the responsible for the quantum computing initiative, to provide us a short introduction about it. So Alberto, I know that you are around. Alberto. Okay, I cannot hear Alberto, and he was here, and I can see him.
Yes.
Alberto, okay. Alberto, I cannot hear you now.
Sorry.
Okay, now I can see you and hear you. Perfect. So maybe
I needed to lift the camera. It's hidden behind the screen. Sorry.
Okay, no problem. So the floor is yours. Maybe you want to share something.
Yeah.
Slides.
So first of all, thanks a lot. Thanks Maria, and thanks Heather for allowing me to steal just a few minutes of your time. I would like to spend just 5 minutes to introduce you to the CERN Quantum Technology Initiative. I have just a couple of slides that I need to start. So PowerPoint is starting, I guess, yes. Okay, do you see the screen?
No, not yet. Okay, now seems that it's trying. No, but still. No, it's not working. Okay, now, perfect, Alberto. So
okay. Okay, sorry. I mean, the network is particularly slow. Again, thanks for allowing me to introduce you to the CERN Quantum Technology Initiative, taking opportunity from this nice event. So just very quickly. So quantum technologies, of course, are becoming very important. Not only at CERN, but all over the world. There are many initiatives, many different projects and activities going on in Europe, in the US, in Asia, in Australia, all over the world to understand what is the potential impact of this new generation of quantum technology initiatives. So we started looking at CERN at quantum computing, quantum technology about 2 years ago. At the time, this was 2018, we organized one of the first quantum computing for HEP events at the time. It was very interesting. There were more than 400 people at the time joining physically and also from external connections, but from all over the world to understand the potential of quantum computing in HEP. Since then, we have understood that there is, of course, a lot of potentially very interesting things and a lot of potential impact that quantum computing, but also quantum technology can give to high energy physics. So we have started a number of initiatives in quantum computing, trying to understand how the different ways of the experiment work today to analyze data can do that in the future using quantum computers. So we are looking at algorithms and different types of quantum inspired approaches. We have looked at what a number of experiments at CERN, not necessarily the LHC experiments, but experiments working with matter and antimatter are doing today that is relevant to quantum technologies, and how to measure quantum states and the interaction between quantum states and gravity, for example. And of course, there is a lot of investigations in the theory field, in standard model, beyond the standard model, where quantum computing and quantum technology can be very, very beneficial. And of course, there is a lot of engineering going on at CERN that was not necessarily designed for quantum computing or as quantum technologies, but might have applications in future generation quantum computers and quantum devices. So we have tried to see whether it is possible to organize all these different activities under a common strategy and measure the impact of these activities for the coming years. So last year, in September 2020, the CERN Council endorsed, after approval from the CERN management, the creation of the Quantum Technology Initiative, which we hope is very bottom-up. It is made of R&D programs on the 4 typical areas of quantum technologies, but in broad collaborations with not only CERN, but with the entire HEP community and with everything that is going on in the world. And the objectives are very straightforward: organize the strategy, understand the benefits, and set up a number of concrete projects to understand the different potential impact of quantum computing, sensing, communication, theory, and engineering in scientific research and in physics research specifically. Of course, education is a very necessary part. Education, training, dissemination, knowledge sharing is a very fundamental part of this discussion. And therefore, not only we are organizing directly events, but we're very happy and very grateful to be able to profit of the many initiatives and channels that the CERN has to communicate and share information and do training, and specifically the CERN Academic Training Services. So I'd like to wish you, to enjoy this event and to pass feedback to us, to understand what we can do together. And for the next 3 years, we are really keen in trying to understand whether quantum technology have a role in high-energy physics and how we can contribute and prepare a future generation of scientists and researchers to use them in the most appropriate way. For any information, there is an early version of the website, quantum.cern, an email list that you can join to have news and information and provide feedback. And I'm very happy to work with all of you in the future and expand our current knowledge for the benefit of everybody. Thank you very much. Thank you, Maria, and thank you, Heather, again for giving me these few minutes. Thanks.
Many thanks to you, Alberto. So then now is the turn of Heather. But before, let me remind you that how we plan to handle the questions. The idea is to handle the questions at the end, unless there is something burning. I think, Heather, it will be helpful for answering questions, but you will have 2 options at the end, okay? It will be via chat, where I will read the questions and then Heather will reply them, and then also raising your hands via Zoom. But then, okay, before giving the floor to Heather, I'm just going to say some words, just saying that she's an experimental particle physicist working on the Atlas experiment. Also, she was here at CERN 7 years working, and then she moved to Berkeley, to LBNL. The key elements of her research program is the development of the track reconstruction algorithms, often using not just quantum computing, also machine learning. So it's also a very nice synergy. And a part of all of this, okay, of course, she is studying, she is studying the properties of the Higgs bosons, and in particular, the interaction of the quarks. And recently, in the last 2018, she got an award from the IUPAP Young Scientist Prize. And even last year, she got a Sloan Fellowship and a DOE Early Career Award. So as you can see, she's a very successful scientist and with the quantum computing technology. So please join me to welcome Heather Gray. I know that we cannot clap as before, but she deserves anyway. So Heather, the floor is yours.
Let's unmute to start the lecture. Thank you so much for the kind introduction. I just want to, I think everyone can see my slides okay. If not, please shout. So let's get started. So today we're going to have lecture 1 of 3. And lecture 1 is going to be entitled Fundamentals. And I just want to call out for these slides today in particular, I used a lot of material from Umesh Barizani and Irfan Siddiqui. And so I'm very grateful to them. All right. So before we dive in, I wanted to take a step back and look broadly at the field of quantum information science. And you can think about it as having a number of different interesting components. And I think probably all of them will be interesting for folks in HEP, things like quantum sensing, quantum networking, quantum cryptography, quantum simulation, and quantum computing. But of course, in 3 hours, there's absolutely no chance that I can actually talk about all 3 of these. So what I'm going to do today is I'm going to focus on just 2 of them, where there's a large overlap with HEP, and these are quantum computing itself, and then also aspects of quantum simulation, which are also pretty relevant for us today. However, I think they're all interesting, and they actually will mention some of them because they kind of all interact and relate to each other. So here is an outline for the lectures. Lecture 1 today, I kind of entitled Fundamentals, but it's going to be a bit more than that. I'm going to talk a little bit about some of the history of quantum computing. You may be wondering, I've heard about quantum computing for many years. Why are we talking about it right now? What took so long? Introduce the concepts of some of the basic units, things like qubits, and then how we actually combine them into quantum circuits. And then I want to spend some time talking about how do we actually make a quantum computer? And we'll start today just talking about the different qubit technologies that are being investigated at the moment. Then tomorrow, we will use these qubits and we will talk about what quantum computers do we have today. And then we will also talk about the various different quantum algorithms that one can make. And then finally, in lecture 3, what I decided to do is to actually focus on some of the things that Alberto was talking about, which is how might quantum computing be useful for HEP? And so what I've decided to do with that lecture is I've pulled out a number of different examples of applications from many different people, and we'll talk about them to get some idea about, you know, why should I be excited about quantum computing? How could it actually be relevant for us? Just one clarification. The goal of these lectures is really trying to be introductory. So if there are any quantum computing experts in the audience, I expect that they may be boring. I apologize for that, but that's kind of not who I've really aiming these lectures at. It's really trying to show to people from HEP who might be interested in knowing what's going on in quantum computing and seeing what might be happening for the future. All right. So on this slide, there are a couple papers which are some of the earliest ideas about quantum computers, and you can notice it's an old idea. Right? These are papers that are coming from Paul Benioff in the 1970s, Richard Feynman in the early 80s. So it's something that people have been thinking about for more than 40 years. And of course, Yuri Manin as well. I'm afraid my Russian is very limited, so I didn't manage to actually pull out his precise paper. But the interesting thing, what these two, for example, you can see in these abstracts that I have here, what Benioff and Feynman were thinking about is to think about making a computer to be like nature in order to simulate nature. I.e., the concept is, we all know there's quantum mechanics. This is how atoms are going to behave. So if we want to do these detailed simulations of atoms and molecules, perhaps the easiest way to do it would be to actually build a computer based on those molecules. And so these were the early ideas. And it's interesting because let's kind of come back. And I would say that if you look at some of the things that we're doing today, we are actually doing some of these ideas. But at that time, it wasn't really about sort of changing the paradigm of computing and doing something different. It was really focused on these physics applications. And so that happened sort of in the early 80s. Then in the 90s, and it kept going since then, what happened and what got people kind of excited about quantum computing, in my opinion, was this invention of various different quantum algorithms. So I pulled out some of the really important ones here. On the top left, this is Shor's factoring algorithm. Probably you've heard about that if you've heard anything about quantum computing. The reason you've heard about that is it's the one that makes everybody worried about cryptography, because all our cryptography relies on the fact that it's really difficult to factorize large numbers. And if one has a quantum computer, it actually has the promise to make factorization far more easy. And so this, of course, threatens all our existing quantum cryptography algorithms. Then there was Grover's algorithm, which came just 2 years later. We'll talk about that in a bit more detail tomorrow, but essentially it's a fast search algorithm that one can do. And this was actually improved by Long in 2001. And so now if you actually generally, the algorithm that's used today is actually called the Grover-Long algorithm. And the reason that these algorithms got people excited is that people started to realize that there was actually the possibility with quantum computers to be either able to do things much faster, or perhaps even more interestingly, to be able to do things that classical computers simply cannot do. And that will come to the concept of quantum advantage or quantum supremacy, which is, of course, something that's been in the news lately. And we'll talk about that actually tomorrow in some more detail as well. And now my slides have stopped turning. There we go. Then people immediately started trying to build quantum computers. And some of the earliest ones were built using nuclear magnetic resonancy techniques. So you can see here a few examples that started in the late 90s and the early 2000s. And these initial quantum computers were really pretty small, sort of 2 qubits up to 7 qubits, which you can see in 2001. There's a link there to a timeline on Wikipedia. Actually, Wikipedia is a fantastic resource for quantum computing. I think that's just because so many people are interested in the topic that there's actually a whole lot of information already there. Now, one thing that people thought, and it's still kind of true today, is that quantum decoherence, the fact that you might not be able to stay in whatever state you actually made, might make quantum computers impossible. And so it really, even at the beginning, even when you started building the first initial quantum computers, one needs something like quantum error correction to allow imperfect computers to be used. And we'll talk a little bit about that tomorrow. So for these NMR quantum computers, what they're doing is using spin states between nuclei within the modules. And these are actually going to be the qubits. And you can use various different molecules to do it. And these ones that they actually made using this technique were never really expected to actually scale beyond a few qubits to do it. So now talking more generally, and I see I have a typo in my title, it's of course meant to say promise of quantum computation. The reason why people are really excited, actually there's not just one, there's a number of different reasons. The first one is that when you start thinking about how to store information inside various different molecules or various different atoms, there's actually the potential to have exponential information storage. And you have extra properties that you can use. It's not really about ones and zeros. You can also think about encoding information through the entanglement that you have through your system. Second one, I've mentioned a bit before. Perhaps we're actually going to find solutions to unsolved classical problems. And there's a whole field of complexity theory that people are looking at and to see if there might be solutions to some of these problems on quantum computers. We don't know precisely what they can do, but there are suspicions that perhaps they can. I also mentioned already that there's this promise to revolutionize cryptography. I'm not sure revolutionize is the right word. Of course, what would really happen is this would threaten our existing cryptographic algorithms. But at the same time, these techniques will allow us to actually make new algorithms based on quantum cryptography, also allow us to develop secure quantum networking. What's maybe interesting for us is the fact that it actually brings foundational quantum mechanics, which we've all known very well since we learned in university, really to the fore with its entanglement, with its exponential power. And it really actually would mean that, you know, quantum mechanics becomes something that everybody's using in their daily life. And I personally find that kind of exciting, that this could be the case. And perhaps it's going to teach us things about complex algorithms and even complexity theory. And some of this will come back on day 3, because already some of the applications that various people are trying for high energy physics, they've actually helped us learn things about existing classical algorithms. And so there's something about thinking about things in a different way that can really improve what you've actually been doing already. And I like this quote. I forgot who I stole it from, but it's one that I think summarizes it quite well. It's really the art of making use of the resources that quantum mechanics gives us. So that sounds great. Why am I not giving you a talk on a quantum computer right now? Of course, it turns out that it's hard. And here are some of the challenges. At the core of the problem is the fact that making a measurement really intrinsically disturbs a quantum system, right? So if you want to have a qubit and you want to know what information you have there, if you're measuring it, you're making a measurement, and we know what this does in quantum mechanics. So if you want to have a nice stable system that can process your information, you really want the system to be totally isolated. However, of course, you need to control the system. You need to give it some data as input. You need to retrieve some sort of result as output. And of course, we also need those qubits. We want them to be able to strongly interact with each other. We want them to be entangled. And so this is sort of a very basic problem. It's really at the root of the idea. It's kind of contradictory what we want to do. Like if you wanted a nice stable quantum system, it would be great if we could leave it alone. But then of course we can't actually do anything useful with it. So that's not really going to help us whatsoever. And so some of the main problems that we have right now are things like decoherence. So this is simply when you put some state on your quantum computer and you wait a while, and then you actually find that you've actually lost the coherence within the quantum computer, and then noise to do it. And so even today, when you start talking about how to use quantum computers, these quantum error correction techniques, these are absolutely critical to be able to do useful things with a quantum computer. I don't think I need the slide, but just to point out that quantum computing often gets portrayed in the wrong way if you look through the popular press, and quantum computing is everywhere in the popular press. People like to think about it as a massively parallel classical computer, right? To do it, with the potential to have exponentially many answers. However, in the end, we are actually, of course, only able to observe one of them, right? You can't actually get all these different answers. So it's not really the case that you can do absolutely everything in parallel and get all those different answers. It's only one that you really get. And so the real speed gains that you can get through quantum computers, these need to come through using interference to actually increase the probability of the correct answer. And this is something that's quite difficult to communicate to people who haven't thought for a very long time about things like quantum mechanics. Okay, so now let's move on and talk a bit about the building blocks of quantum computers. And there are 3 of them. We're going to start with what is a qubit. Then we're going to talk about what is a quantum gate, which allows you to do things with qubits. And then finally, how do you assemble these into a quantum circuit, which would actually be able to perform one of these different quantum algorithms. So qubits. These, of course, are the basic unit of quantum computation, and they are essentially the quantum analog of the bits that we know well in computers today. And if we want to think about a simple example, put in your mind a hydrogen atom, and let's say that we want to use the ground state of the hydrogen atom as 0, and we want to make the first excited state be 1 to do it. And that's actually not so far from the truth about how we actually can think about making qubits. And as you see, as we go further along, there are actually many different ways that we might be able to consider making qubits. And that's why the field is actually quite broad right now. Of course, more generally, it's not going to be a hydrogen atom. It can be any quantum state, which we'll call psi. And then we can have two coefficients, alpha and beta, which will be in front of our 0 and 1 unit vectors. Of course, what this really is a unit vector in a Hilbert space. And then when we go about measuring our qubit, right, retrieving our information from the quantum computer, if we have a state with those coefficients alpha and beta, what we're going to get is we're going to get 0 with a probability of alpha squared, and we're going to get state 1 with a probability of beta squared. And as I said before, when you do this measurement, you really are disturbing the state. And what this means is that you cannot really determine both alpha and beta in a single measurement. And as I said, there are going to be lots of different ways to realize these qubits, things like photon polarization, also spin. And one of the representations, which is kind of useful to do, is going to be a Bloch sphere, which we're going to come back to, I think, a bit more on the next slide. Now, of course, thinking back to quantum mechanics, one can express qubits in many different orthogonal bases, right? So you can make a transformation where you define some new state with various different coefficients. And then, of course, you can make a transformation, and then you could think about performing your measurements in that different basis. Some of the standard bases that get used are 0 and 1. There's also the sign basis, where you can see the definition here. And of course, you can think of any orthogonal bases that you might want to use to do it. Now, you can see here this Bloch sphere, which is kind of a convenient way of representing the different states. And when you think about it, you may say for a second, hold on, there are actually only 4 different, sorry, just fixing something, 4 different coefficients here, because alpha and beta are going to be complex numbers. However, it's actually only the relative phase between the coefficients of the 2 basis vectors that has any particular meaning. And so it ends up being redundant in the definition. And so once you make some choices, then you end up with 3 different pieces of information. And that's actually how you can make this representation on the Bloch sphere. And you can see here some labels. For example, here is the 0 state, here is the 1 state, and you can see various other ones and these different angles that you might want to define. Sorry, I've lost the ability to change slides. Okay, there we go. Okay, no, we have really lost the ability. Sorry, everybody. Here we go. So you could also generalize this, of course, to any qubit system using a tensor, generalize our 1 qubit to a 2 qubit system using a tensor product to do it. And of course, you could think about generalizing this even further using all the way up to n qubits to do it. Now let's think about for a second a 2 qubit system. So let's pretend, for example, we have 2 electrons in a hydrogen atom. This would actually give us 4 different states, and it will give us 2 bits of classical information. So here you can see we can write out our state as a combination of 0, 0, 0, 1, 1, 0, 1, 1 with all the different coefficients. Or if you actually ask the question about how much information you have, it turns out that there are only 2 bits, and the rest of this ends up being inaccessible to measurement. Now, one thing that you may wonder is, why do we actually have to stick to qubits, right? We have an atom that has many different energy levels, and yes, that's correct. You can actually very easily think about extending qubits to qtrits or even qdits to do it. And so this is something that people think about, but I wouldn't say that it's the mainstream of development right now. Most of the time, things are actually focused on these existing qubits. Quick reminder, not all 2 qubit systems can necessarily be decomposed into pairs of qubit states. One of the famous ones, which you know well, are the Bell states. Of course, there are 4 of these different Bell states, and they're maximally entangled. And what happens here is that if you measure either qubit, then you can find that, sorry, if you measure the first qubit and you find that the measurement is 0, what you're going to see is that the second measurement is always going to be 0. And so this is how they're actually maximally entangled. And this is one of the 4 different Bell states that we have. And this will actually, by the way, be true in any different orthonormal basis. Of course, these Bell states, they're pretty famous. They played a key role in the EPR paradox back in the days where people were not trusting that quantum mechanics was really a true theory, and was trying to be used to actually argue towards theories of hidden variables to do it. Another important thing from quantum mechanics is the no cloning theorem. And this one, when you hear about it for the first time, at least when I heard about it for the first time, I thought, oh man, this sounds like we can't do anything with quantum computers. And of course, what this says is that it is impossible to make a separable copy of an unknown quantum state. Okay, so if you have some quantum state sitting here, you can't actually make a copy to do it. And by the way, of course, the proofs of this are quite fun. Things like, you could enable communication at a speed faster than the speed of light, which would be very convenient to do it. However, you need to look at the words carefully, because it does not mean that we cannot reproduce a specific state. It only means that we cannot make a copy of an unknown state. So for example, if we had some state sitting on our quantum computer, we couldn't make a copy of that unknown state to do it. And so when you think about this, you might ask the question, does the no-clone theorem mean that it's impossible to store quantum information, or that it's impossible to correct errors? In the end, the answer actually turns out to be no. Although we cannot copy qubits, it turns out that you can actually think about spreading information from a single qubit onto multiple qubits. And that actually enables us to still be able to use qubits to do various different things that we would want to do. So that's a few words about qubits. The next ones are the quantum gates, and these are used to manipulate quantum information. For example, to operate on our qubits, because it's pretty boring. We encoded some information, we actually want to be able to do something with them. And of course, we talk about quantum mechanics. So this, whatever we want to do, this needs to be unitary. And so our quantum gates are simply the unitary operators. And then once we have the quantum gates, you can actually combine them to produce a quantum circuit. And that's an example of one sitting down there. We'll come back to that a little bit later. But now I just want to go through a few examples of some of the different ones. And we can kind of start with the quantum gates for single qubits. Here are some of the famous examples. So this is the Hadamard gate. And this is essentially a rotation by an angle pi around the pi/8 axis in the complex plane. Or maybe a simpler way to think about this gate is that it will map from the 0,1 basis state to the ± basis state. Now, because we're going to use them in circuits, each one has a symbol. So you can see the symbol there. It's kind of straightforward. You get an H for the Hadamard gate. And of course, you can also do it with a matrix representation. So the matrix is also written up above there to do it. And Hadamard ends up being a gate that's really quite commonly used. The next one is the NOT, or the Pauli X gate. It has two names and two symbols that go with it. And what that one does is it actually maps what you had in 0 to 1 and what you had in 1 to 0 to do it. And so it's the sort of quantum equivalent of a NOT that you could think about classically, where you're essentially just switching around where the information actually is. Then the third one is you also need to worry about the phases that you have. And so this is the phase flip, or the Z gate that you have. You can think about it being kind of a NOT gate on the ± basis. Essentially what it's doing is it's actually the probabilities of measuring 0 and 1 are going to be unchanged, but the phase of the quantum state is going to be changed. And you can, of course, generalize this one. It doesn't have to just be a phase flip. You could think about having various different phase rotations where you add in some sort of arbitrary angle instead. Then moving on to 2-qubit systems. Here are some examples. For example, here is the C0 gate, which you're going to actually see a whole lot in the various different circuits that we have. And what this one does, it will flip your second, so your target qubit, if and only if the first qubit is going to be 1. Sorry, to do that. Then for the controlled Z, what that one does is it's actually going to apply a Z gate to the second qubit if the first qubit is 1. And so similarly, you could imagine you could make various different controlled gates for various other pieces of information. And finally, next for the 2-qubit system is going to be the swap gate, which you can use to actually swap the information between 2 different qubits. As you're noticing, there's sometimes various different symbols. And so in some cases here, I'm showing you multiple symbols for the different gates. Then 2 of the very well-known gates are known as the Toffoli or the Fredkin gate. And you can see here that these ones are going to be operating on 3 qubits instead of 2. And so for what the Toffoli does is if the first 2 bits are 1, then the third bit is going to be inverted. Okay, so you can think about this as some sort of control gate, right? Because if you can change what you have in the first and the second bit, then you're going to act differently on the third bit. And thinking about it, it's pretty easy to imagine how this might actually get generalized to an n-bit version of that gate. Then the other one is the Fredkin gate, or it's also known as C-swap. And what this one does is that if your first bit is 1, then you can swap the second and the third bits. Something to notice here is that both of these gates are actually reversible. And this is something we'll come back to a bit later. Again, thinking back to all those properties of quantum mechanics, it actually turns out that you need everything that you are allowed to do in quantum computing will actually need to be reversible. Otherwise, we would end up violating the rules of quantum mechanics. So now, of course, we want to go a lot further. We don't want to just have qubits and gates. We want to think about building a programmable computer. And what that means is that we need to be able to do any series of quantum operations. And so what you need to do is you need to choose a set of universal quantum gates. And these are not quite what you might think by the name. And so it's not quite universal in the sort of strictest sense of the definition. What it actually means is if any unitary operation can be approximated to an arbitrary level of accuracy by a finite quantum circuit using only those gates. So what it means, right, is that you don't necessarily have to be able to do everything. You just have to be able to get to any level of accuracy using those gates, and that can be regarded as a universal set. Almost any unitary transformation on a 2-qubit system can be approximated by a sequence of CNOT and single qubit gates. And you can actually do some calculations, and a number of these being done. And here's one which shows you the number of gates that you would actually need. And this is known as the Solovay-Kitaev theorem. There are a bunch of different universal quantum gates. Here are some of the sets of them, things like phase and rotation and CNOT, Toffoli plus Hadamard, CNOT, Hadamard, and phase flips. And so it's not unique, whatever set you might have. There are a number of different sets that one could consider using for universal quantum gates. And then finally, it's not the case that your set of universal quantum gates are the same as your universal classical gates. They're actually different. And so that's one of the sets that you might have thinking about classically. Okay, so now we have qubits and we have quantum gates. And so what we want to do is to combine them to produce quantum circuits. The logic that we have will really flow from the left to the right. And the lines that you see in the diagram, that's actually indicating the individual qubits. So thankfully, quantum computers don't have too many qubits right now. And then the quantum gates are either indicated by boxes, if it's something complicated, or it's indicated by those different symbols that I was showing you. But you can follow the diagram simply from the left to the right, and you can actually figure out what it's doing. So let's do an example. Let's go back to that Bell state that we were talking about. And then you can, and this is actually the circuit that one would use to be able to generate it. So we have 2 gates here. We have the Hadamard and we have the CNOT gate. And so the easiest way to think about it is, let's imagine that you sort of had an input of 0, 0. then in step one, what you're going to do is after you've just applied the Hadamard gate, you're going to get 1 over square root 2, 0, 0, plus 1 over square root 2, 1, 0. Then after you apply the C0 gate, then you end up getting 1 over square root 2, 0, 0, 1 over square root 2, 1, 1. And here, as you can see, as promised, we've actually gone about generating our Bell state. And the way to think about this is the fact that this application of the C0 gate, this has actually gone about entangling our qubits so that we end up with this entangled Bell state system. And then here's a maybe more complex example. I'm not going to go through it in quite as much detail as before, but this is how one might actually go about building a circuit to construct the Toffoli gate that we were talking about from the various different single qubit gates that we had before. And as you can see, as you start doing more and more complex things, you end up getting a bigger and bigger system with more and more gates. So as I mentioned before, all quantum evolution, of course, needs to be unitary. And people were initially worried that this put really constraints on the capabilities of quantum computation. It turns out, though, is that you can actually make a reversible circuit for any non-reversible circuit. And here's a simple example, well, not that simple, where you can see on the left, you have some circuit C. You can actually end up making this reversible by adding in some extra bits there, constructing this new gate C, and you end up with these garbage bits. And then, of course, if you want to make a clean circuit where you just want to get the information that you're actually interested in, these qubits, which are labeled as X, you can actually apply the circuit on the right, where you actually end up doing a cleaning of it to really get a clean reversible circuit. And so this was quite a relief once people figured this out, because it meant that we could actually really build quantum computers that would do very useful things. So here's the circuit model for a quantum computer. It's really a Hilbert space of n qubits, which can be decomposed in many cases into subsystems. We need some initial state. We need a finite set of unitary quantum gates. We need some way to do classical control. And then we need to do readout. And so now for the last bit of the lecture, I'm going to sort of switch topics a little bit and talk a bit about how one goes about actually building quantum computers. So in general terms, there are kind of two different types of quantum computers that you may hear about. They are analog quantum computers. And what you do here is you really initialize some sort of quantum state. Then you want to really directly control the Hamiltonian of that state to evolve it to solve some sort of problem. And examples of these include quantum annealing, adiabatic quantum computing, and direct quantum simulation. And so these analog computers, these were really true to the initial ideas of quantum computing that came from Benioff and Feynman right at the beginning. But of course, mostly what we've been talking about now are the digital quantum computers, or the gate-based or the universal quantum computers, where what we do is we really want to break down the problems into operations, which are gates, and we want digital outcomes for certain input states. And these, of course, are much more similar to the concept of classical computers, but people are trying to build both. So saying more about the analog quantum computers, where you have the system of qubits in some sort of initial quantum state, and then we really change the Hamiltonian to encode the problem in the final Hamiltonian, and then the final state is the answer. And so in some cases, you'll stay in the ground state, and this would be things like adiabatic quantum computing. And in others, in quantum annealing, you're actually trying to move between the different states, and that's actually how you find the solution to your problem. It turns out that for highly complex Hamiltonians, that analog quantum computing can be shown to be equivalent in computational power to gate-based quantum computers. However, existing quantum annealers, the ones we have today, really have quite limited choices for the Hamiltonian. And then, of course, you can use them for direct simulation, where you set that Hamiltonian to be the system of interest. And evolution really models that system. Now, turning to the gate-based quantum computers, there are a set of criteria which were set out by DiVincenzo about what you need to be able to build a gate-based quantum computer. So you need to start with a quantum two-level system that can be employed as qubits. You need some sort of ability to be able to initialize those qubits. You need sufficient decoherence time to complete the calculation. It's not going to be useful if your state is completely incoherent before you've actually done your computation. You need a set, as we were talking about, of universal quantum gates. And then you need some way, some ability to be able to measure those quantum bits. And so now we want to look through some of the current technologies that people are using to build quantum computers. So this slide is a nice little cartoon summarizing some of the different topics. So there are the well-known superconducting qubits, where you have a persistent current in a superconducting circuit. There is also using the magnetic field of the electron. There will be photon polarization, and there will be atomic internal states. And so some of the general ones. Then on this slide, which is from a very nice report about quantum computing a couple of years ago, it actually summarizes 5 different types of qubits. And it does some sort of comparing between them. You know, how do you get to the physical qubits? What is the lifetime of the qubits, the fidelity of the gates, the operation time, etc. Because one of the things that becomes tricky in comparing quantum computers is that you can just compare the number of qubits, but that doesn't tell you the whole story. All these other features end up being really important. And I haven't actually checked in detail, but I'm pretty sure this will be already out of date, given the rapid progress in all these different technologies in the field of quantum computation. And that's one of the tricky things. There's a huge amount of money being invested, and it means that things are really changing month to month right now. At the same time, of course, that's really quite exciting. Here's a nice slide I stole from Jean-Roch, which is actually comparing between the 2 different types of computers, the digital and the quantum annealers, to do it. And the reason that it's a useful slide is that when you're comparing them, which is something we'll come to tomorrow, the quantum annealers have far more qubits. However, because they're actually only able to solve really specific problems, comparing directly the number of qubits is not necessarily the way that you want to compare them. And so that's something to keep in mind. So now the first technology we'll talk about, and just a disclaimer, I'm no solid state physicist. So of course here we're going deep into solid state physics. And so there will of course be far more information than I can show. These trapped ion computers are one of the earliest types of quantum computers. And the idea is that you want to strip atoms of their outer electron, and then you take these positively charged ions and you control them by electric fields in ion traps. And so there's kind of a picture on the right there showing you the trap that you might actually have where you have the ions in it. Of course, these are going to need to be contained in ultra-high vacuum chambers. And then you need to use lasers, which can actually cool your ions to really low temperatures, thinking, well less than a milli Kelvin. Now, of course, you don't want to just make an ion trap and sit your qubits there. We need to actually control it. And the way that you do it for trapped ion computers is you will actually use laser pulses or microwave radiation. And you can actually use this to be able to couple the different ions together and to do whatever quantum computation tasks you might want to do. Bottom right, that's actually a picture showing a little bit how this could look. So it really looks like a physics experiment, but of course what it is trying to be being a quantum computer. Now, trapped ion computers, they get less press than the superconducting ones, which I'll talk about next. So I wanted just to make a couple comments about what they look like today. So at the moment, we've just very recently reached a single qubit coherence of up to an hour. So it means if you have 1 qubit, it can be coherent up to an hour. They also have very high single and double qubit gate fidelity. And one of the things, and we'll talk about this a bit more tomorrow, is that some of the designs allow full connectivity between the qubits. What that means, right, is that you can actually have information that can pass between the different qubits. You need them to be physically connected. And this won't necessarily be the case for all the different computers we think about. In some cases, the connectivity can be really low, and it might be just the 4 nearest neighbors versus all of the different qubits. So one of the companies, and there are many, or basically each technology is being followed by different companies, is called IonQ. And they're producing quantum computers using trapped ion systems of the ytterbium ions. And the most recent one that they've actually made is 32 qubits. And in fact, in the past couple of days, IonQ became the first publicly traded quantum computing company for for an offering of $2 billion. So yeah, quantum computing is certainly something where there's a huge amount of investment. Now, moving on to superconducting qubits. These are currently one of the most commonly used technologies in our current era, which has this name, which is this NISQ, noisy intermediate, and now I'm getting my acronyms wrong. I will come back to that later. And what you do with a superconducting qubit is you create an artificial atom using superconducting materials, and in particular, something called a Josephson junction. There's a picture on the bottom there showing you how it works. You have two superconductors, and then there's a small piece of insulator sitting between them. The idea is that that makes it really difficult to be able to move between them, but not impossible. It's basically making you a weak link. And so typically what it's made of is aluminum oxide between two different layers of aluminum. And what you want is your Cooper pairs in the superconductor to be able to tunnel through the insulator. This is really what allows you to actually make this into qubits. In many cases, you can actually build arrays using similar processes to manufacturing integrated circuits. And you can manipulate states, again, using microwave radiation. They also need to be cold, typically in dilution refrigerators, but below 100 millikelvin. And there are actually three different types. There are the phase, the charge, and the flux qubits, which are different ways of actually making superconducting qubits. So there's a sketch on the right showing you what a charge qubit and a flux qubit looks like. The X is really the label for the Josephson junction in the circuit. So to make a charge qubit, what you need is a Josephson junction, a capacitor, and some sort of voltage. And what this does is you end up making a Cooper pair box, which is labeled there in red. And the way this becomes a qubit is you're having superposition between having either 0 or 1 extra pairs in this box to do it. For a flux qubit, on the other hand, what you need is a loop of Josephson junctions and some sort of external magnetic flux. And you store information through the superposition of currents circulating either clockwise or anti-clockwise. Finally, for a phase qubit, here you have a single Josephson junction, and you're really looking at the quantum oscillations of the phase difference between the different electrons. Now, one type of charge qubit is known as the Transmon charge qubit, and this is one that's actually used pretty commonly. And the way it came into being is that historically charged qubits suffered from severe problems with noise, and Transmon ends up being much more robust towards the noise. So the way that you can think about it is that you have some sort of quantum harmonic oscillator, and this has a resonant frequency, right, which you can calculate for it. But the problem is, because it has all these different levels, this can't actually be a qubit because the levels are evenly spaced. So you wouldn't know if you went down from level 3 to level 2. So you can fix this if you make it into an anharmonic, and that's actually where the name Transmon comes from, by adding a nonlinear inductor, and this, of course, will be our Josephson junction, and you can really see the circuit on the right, which does it. And this means that your levels are not evenly split, which allows each transition to be uniquely addressed. And so far, what we use is we actually use just level 0 and 1 for the qubits. But of course, you could see here, there's a very natural extension if we wanted to think about going to more. At the bottom there, there's a picture which shows you the evolution versus year into the lifetime of various different types of qubits. And you can see it's a log scale, so you can actually see just how quickly the lifetime has been increasing over the different years. A couple words on quantum annealers. These are actually, again, using superconducting qubits. But what you want to do here is you want to apply some sort of magnetic field, which will actually bias the different minimums for the different qubits. And then you want to also be able to do a coupling between the different, the strength of the different qubits. And what you can do with the quantum annealers of today is they're very good at solving one problem, which turns out to be a very common problem in computer science, which is known as QUBO. It's quadratic unconstrained binary optimization. And you can really encode this. And if you can encode your problem using Cubo, you can actually run it on a quantum annealer. Now, quantum annealers are very controversial. I pulled out one article there. And I think the way, if we want to just summarize it in maybe one sentence, the reason that they're controversial is that they work very well. However, we don't expect to obtain a speed up over classical computation with these different quantum annealers. And so that's why people sometimes you might hear saying that these are not quantum computers, is simply because some people think that we should only use quantum computers if they're going to end up being faster. Now, one of the technologies that's been in the news recently are photonic quantum computers. They're also known as boson sampling. And this is essentially a quantum computer where you can encode the information in the polarization of photons. And to make a quantum computer, it looks like a large optical circuit. You really construct the circuit from squeeze photons, beam splitters, and photon counters. And so here's a sketch here showing you what it would look like. And that one we'll talk about tomorrow because there's a very big one that was built recently in China that had some very interesting results in terms of quantum advantage. Silicon-based qubits are something that have attracted much attention. The original ideas are from the late 90s. The reason that people are interested about this is if we can actually get it to work, we might be able to use many of our existing technologies that we have for producing large silicon circuits and produce larger quantum computers. So what's typically done is you would store the qubits in the nuclear spins of phosphorus atoms in silicon. And there have been demonstrations of using one in 2012 and two in 2019 qubit operations using phosphorus. There's also a slightly different way that you might be able to do it, actually using quantum dots, which are an interesting technology in themselves for other applications as well. Finally, there are topological quantum computers. And this is take some complex ideas from mathematics. And you want to really exploit topology, which would allow you to build quantum computers that are more robust to outside interference and noise to do it. The qubits for these would be something called the anneons. These are quasi-particles with statistics interpolating between fermions and bosons. One route to potentially realizing a topological quantum computer would use Majorana particles. And you could do this by forming two Majorana particles, or you can sort of think of them as half electrons on both ends of a semiconductor wire wrapped with a superconductor. And then what you do is you make the qubit by encoding the information by swapping the positions of the particles on the wire. And this is actually a strategy that has been pursued by Microsoft, of one of the big tech companies. There was a bit of drama recently. There was actually a claimed observation of Majorana zero modes. There's the paper. There's also the retraction because it was actually found that there were some issues with the analysis of the data. So that brings me to the end of today. I think that quantum computers hold exceptional promise to transform computation, but their realization requires overcoming many significant challenges. Try to give a brief introduction to some of the historical developments of the field of quantum information and quantum computing. I showed you that qubits are the basic units of quantum computation with a wide range of possible realizations, things like trapped ions, superconducting qubits, photons, and topological quantum computers. Quantum gates, of course, operate on qubits to change their states, and we combine those gates into quantum circuits to be able to perform quantum algorithms. I showed you again all these different technologies, and tomorrow what we're going to do is to try and really bring this together by discussing some of the current quantum computers, quantum algorithms, quantum advantage, and quantum error correction. Thanks.
Thank you very much, Heather. It was a fantastic presentation. So now is the time for the questions. Please, if you have any questions, just write in the chat or raise your hand, so then I can give you the floor. So for the moment, I cannot see questions in the chat. Okay, I can see a raised hand. Oh, no. Sorry, I'm going to put the gallery because, okay, from Nicole, please go ahead.
Hi, I have a kind of naive question on the Transmon slide.
Let me try get back to it for you.
Thanks.
I'm doing the thing where I can see presenter notes, but somehow it just, uh-oh, that's not good. Hold on. Well, go ahead and ask your question, or maybe you need to see the slide to ask your question.
No worries. For the
Yeah, there you go.
like only keeping the 0 and 1 state, I was wondering how you prevent the circuit from going to the second state, or like if that's like a failure mode, like the leakage from.
So my understanding is that it's okay if you go to the second state. Of course, you'd lose your information or things like that to do it, but you're not, because you end up having this difference in the energy levels, it's not going to corrupt the information that you get out. So I think you would sort of count that together with things like decoherence of your system, right? You would lose the information, but at least you wouldn't be confused about it. This would be the point.
That makes sense. Thanks so much.
Okay, also I can see a question from Dimitrios. Hello, only one question. If 0 gets to 0, why using swap?
I'm not sure I understand the question, but let's go back to the swap. Probably there was a typo. I said what he just wrote. If 0 gets to 0, why use swap? I'm not sure I understand the question. What swap does, right, is it swaps the 2 qubits.
Okay, he is replying here in the chat. Maybe Dimitrios, if you want to talk, please.
Yeah, sure.
Okay. I don't know if he is writing, but he was saying, I apologize to make it clear. I don't see more comments. So Dimitrios, if you want to say something. He said, just a moment. Okay. Also Maria Dimo, okay, I will give some time to Dimitrios. So Maria Dimo was saying, I like to raise a hand, but I can't. So go ahead, Maria.
I am sorry, I just come out of a Zoom meeting where I could raise hand. Now I don't know what happened. Excuse me, thank you very much for this lecture. Looking forward to the other two. I have a man off the street kind of question. If quantum physics is linked to non-determinism, how are we so sure about the results we are getting with this technology? Sorry.
Okay, no, it's a good question, and it sort of relates to some of the things that I was trying to talk about, right? That really controlling these systems is quite hard to do it. And so I think that the answer is that you have to construct these computers very carefully so that they actually become deterministic. But of course they're not. And so often what is done, especially today, is if you want to make a measurement, you might end up running your experiment there multiple times. And then you have a probability of getting your right answer that would increase. And so you have to be kind of comfortable in terms of thinking about the probabilities of the outcomes and using that to achieve what you want to do. So it is, you're right, it's a very different way of thinking compared to regular computation, where everything is completely deterministic, at least mostly, until your computer crashes.
Thank you very much. Thank you.
Did we get the comment from Dimitrios?
Not yet. So, okay, but now I can see one raised hand from Antonio Gilardi. So go ahead.
Hello. Hello.
Hi. Yes.
It's just a ground question for me. Is like I can imagine because you give a nice nice idea of a qubit, like a state change or something close to this. But I can imagine a gate like not like a cooling or an exciting of an atom, but it's a kind of difficult for me of thinking other kind of gates. Can you give a kind of example of how a gate is like, how is it composed by? You see what I mean?
We'll come back to that a bit more tomorrow when we talk about, because all I've done so far is I've showed you how we make a qubit for a quantum computer, right? And then, of course, the next step is how do you actually operate on that information? But the answer is going to be that it really depends a lot on all the different technologies that we're talking about, right? And so, for example, some of these cases is, let's go back to one of these slides. You can still see my slides, right? To do it. Yeah, for example, you know, the way that you can actually control and do things here is you need to use the different lasers to do it. And so you've got to really think about, you know, we were talking about these different gates. You want to do a CNOT, right? You need to, for example, if one bit is this way, you need to do something to the other bit. And so the answer ends up being quite complex and will depend on the different technologies, but we can talk a bit more about that tomorrow. It's a great question.
Thank you.
Okay, so following with Dimitrios, finally he said that I will follow the next lecture tomorrow to formulate my question in a better way. Thank you. But
he can also, Dimitrios, you can also send me an email if you feel like it. That's also totally fine.
Yes. Also, but in any case, we have more questions. So one from Bhavna Prasad, I hope I say properly. Thank you for the talk. I have had this question for a while. Is it possible to have some sort of noise engineering for encoding the losses in the system we are considering, or to link the decoherence to losses in the system?
So to link the so wait, can you read it again? Sorry, I didn't quite get it.
Yes. Is it possible to have some sort of noise engineering for encoding the losses in the system we are considering? Or to link
Yes. Okay.
Yeah.
Yeah, so I think the answer is kind of yes. And that relates back to the topic about error correction, right? What we're really trying to do with error correction is firstly to detect, did an error occur? And in fact, you can even do better than that, is you can actually design a circuit that will also automatically correct for any sort of error. So it's not quite what you were asking, right? Which is saying, can you do something maybe more general in terms of doing it? But you can actually work to protect your algorithms against these sorts of things because you know that they're going to happen, and they do happen basically all the time.
Okay, I think you answered his question. If not, maybe you can say something else. But now I have another question from Sahil Mathur. Hello, my question is where we use the quantum computing gates while using quantum computing.
So if you want to run a quantum algorithm, what you need to do, right, is first you want to actually encode your information on your qubits, and then to do something, right? So for example, to factorize a prime number or to do a search, you need to actually use the gates, which will do the steps of your algorithm. And so that's what you would do is you take your qubits, you apply the gates, and then after that, you'll get the solution to whatever problem you're trying to solve, at least probably.
Okay, then I can see a raised hand from Paris. Please go ahead.
Hi, hi Heather, great lecture.
Hi Paris.
Hi Heather. I have a question regarding preparing the initial state. For example, this trapped ion picture. How can we be sure that the state that comes out is really 50-50 and it's not 51-49, 60-40 in terms of probabilities? How do we know that we actually prepared the initial state in exactly the, you know, in the mathematical 50-50 that we write down?
That's a great question, and that goes well beyond my knowledge. If I had to guess, I suspect that the way that we've become confident of that is that they must have done a number of tests to actually check that their encoding really gets close. But you're right, to get really to that level of precision, that's really difficult. And of course, you don't know on each specific experiment if that might have happened. I guess the way that we try to protect against this, especially right now where things are pretty noisy and unstable, is by performing it a number of different times. And so I could imagine, right, that you could make an experiment to specifically check that, right? We could just entangle it, just measure it, do nothing. And you could actually experimentally check it. But I agree with you, knowing this a priori is something that's really quite difficult to think about doing.
Thanks, Heather.
Sorry, here more questions. So hello, from Tassos. Hello, if we cannot use silicon for the quantum gates, in what material devices can we use to create the gates? Thank you.
So actually we don't know, and that's one of the topics that I talked about just briefly today. There are indeed ideas about making quantum computers out of silicon. And in fact, that's really attractive to do it, because then we would be making the gates in silicon. But for each of these different technologies that I'm showing you, you actually have to make gates in a very different way. So for example, here where we're looking at the photons, you actually need to use these different beam splitters and beam mergers to actually make those gates, to actually get to construct your circuit. So it really depends on the technology that you're talking about for the quantum computer.
Okay, so then going with Javier Ferrer. Thanks a lot for the talk. So do we need an amount of qubits at least as big as the result we are trying to compute? Is there any way to interpolate or split the problem, or sorry, it's moving the chat because I'm getting more questions, so it was difficult to read, sorry. Is there any way to interpolate or split the problem, or does everything have to be there to benefit from the entanglement? Oh, sorry, that I didn't understand.
It's okay. I think I got the question.
Oh, yeah.
That's a great question. And of course, the answer is that because all the computers that exist today have very limited number of qubits, you absolutely have to find a way to break down your problem to be able to solve it on a quantum computer. But you're right. If you do that, of course, you're losing the entanglement between the different pieces. But many of the applications, for example, some of the ones that I'm going to show you on the third day, those are actually breaking down the problem. So some of the work I did, for example, on D-Wave, there's actually software that will do it for you. So we basically encoded the full problem that we wanted, and then it actually would break it down into sub-problems, which we could actually run on the quantum computer, because of course the number of qubits that you have accessible are very limited. And then you have to combine it back together again. So it adds a big overhead, but that's what one needs to do at the moment.
In fact, Javier is saying thank you for the reply.
Pleasure.
From Furkan Jadisi, thank you for your presentation and talks. I didn't get it how the gates change the information when we apply the gates on the ions or the other quantum computer types. I mean, let's say we apply C0 gate, how are two qubits become entangled in an atomic way?
So that kind of goes a bit beyond what I was trying to show today. And I don't think I have a good example explaining it for the ion, but I think maybe the photon is perhaps an easier way to think about that, where you think about having the polarized photon, which is the side we're on, and then you can actually think about going through a beam splitter, right? And so you have one photon, you go through a beam splitter, and you're going to have two photons, which are going to be entangled with each other, right? Then you can go on further. You might come to another one of these various mirrors and things, and you come across, and that way you can actually develop entanglement through the system. So I don't have a good slide to explain that for the trapped ion, but that would be how it would work for the photons, for example.
Okay, so from Julian, sometimes companies release numbers for the fidelity of their state preparation and gates, so they must have performed tests to get these numbers.
Yes, I believe they do. And in fact, usually with each of the releases, and for example, that's the one that the trapped ion folks like to show because they end up having fantastic numbers for things like fidelity. Unfortunately, and this is one of the things I find difficult in the field, companies are not like academics, right? When we publish a paper, we try to provide all the information about everything. Sometimes for this, you'll just get a press release where it states the number and it doesn't provide you with a link to the paper, which does it. So unfortunately in this field, sometimes it's hard to find the information about how precisely they determine that number. And of course, that's a concern, right? When you're thinking ahead to the future, you do really want to be sure that everything's being measured, for example, in the same way.
He say, I agree with you, Heather. That's unfortunate. Thanks for the lecture. So now from Andreas, when and where can I watch the recording? Okay. Don't worry, this will be recorded, and I don't know, because it depends also with our audiovisual support, but it will be published in Indico, and at the same time it will be recorded in YouTube. So we have a YouTube channel for CERN lectures, and you will be able even to see these lectures there. In any case, just if you send me an email, I can just ping you exactly when it is uploaded. Then from Slian, great lecture. I have a technical problem. You mentioned the lifetime of the coherence. For example, for the trap ion is about 1 hour. What are the key issues for the coherent? For a mature quantum computer, does that mean the coherence should last until the next manipulation, chain of the quantum state?
Yeah, so I don't have the details about exactly what determines it, but when I will post the slides and you can actually see the links. Sorry, I'm finding this slide. It has actually the link to where they did the measurement of the 1 hour coherence. So there are some details there, so you can have a look through that afterwards. But yes, it really does mean what you say. If you have a coherence of only a certain amount of time, whatever operation you need to do on your quantum computer needs to be actually completed within that period. Otherwise, you're going to end up losing information. And just to be clear, right, that's a single qubit coherence. And for example, the most recent, the largest trapped ion computer we have at the moment is 32 qubits. So the coherence of that is going to be a lot less. So yes, as I was saying, this lack of coherence is something that really limits what one can actually be able to do with quantum computers right now.
And then from Laurent, most of the gates you mentioned make change based on the states of other qubit. But you also say that reading the state of a qubit may corrupt it. So even if we think in terms of probabilities for states, gates may make changes in a non-causal way, making reasoning by inference difficult for building valid algorithms.
So there's a little bit of a difference. So we don't use the gates to read the qubits, right? What we're using the gates for is to manipulate the information within the quantum circuit. And at that point, each of our qubits is in perhaps some sort of probabilistic state. It's only when we read it out and make the final measurement, right, that we collapse the wave function and we are actually in some specific value. And that's not necessarily done by the gates. You don't want to do that in the middle because, as you say, if you did that, then you would end up messing up your result. That's something that we do at the end when we want to get the result.
Okay, thank you. So from Vivek, which book do you recommend for quantum computing?
So I'll put some references in slide 3. There's, of course, depends what you're interested in. There's classics, things like Nielsen and Chung, which can give you a really good overview. But of course, as you can see, the field is moving extremely rapidly. So if you're interested in quantum technologies and current quantum computers, I don't know of a good up-to-date textbook that exists. One really needs to actually follow the research to see that. There are also some great lecture notes from various people, for example, John Preskill, Scott Aronson, etc. I'll have a list on day 3 of various extra material for anyone who's interested.
He say thanks for the information. So another question popping up from Gernot. When there will be a physical quantum computer at CERN?
I guess that's not for me. I guess
neither for me. I don't know if Alberto Di Meglio is around and he can say something.
Well, let me say something. So there are actually a number of companies that make small commercial quantum computers right now that one can buy for sort of tens of thousands of dollars. So you could go and buy one right now. However, of course, those are extremely limited. And I guess what you're really asking is at what point in time might one get a useful quantum computer at CERN? I think the question of when we'll have useful quantum computers in general, the answer to that is not known. And there's a super wide range of predictions. Some people say this will be within a few years. Some people say it will be never. So I think truly we don't know just yet. But there's promise that it might be somewhere within a decade, but we don't know. We have all these problems that actually need to get solved to be able to do that.
Thanks, Gisei, as well. So I don't know if Paris want to ask something else because I can still see the raised hand.
Sorry, it was left up there. I'll pull it down.
Okay. So I'm not seeing more questions. So I think, okay, if you want to say something else for tomorrow or just Heather, the floor is yours.
Yeah, no, so I think that's it. If there are any other questions people have, feel free to drop me an email because then I can try to cover it tomorrow or the next day, depending when the email arrives. But yeah, thanks everybody. It was fun. Thanks for the questions.
Oh, someone is asking again. Could you post those books' names in chat box if possible? I think it's better if we do it via email.
Indico. Let's put it in Indico.
It will be lost. So yes, you can maybe pass to me or maybe create a slide with the name of the books. So maybe in the next lecture, everybody will see. So in case they
I can make a slide. That's no problem.
Okay. Another 2 questions, but I'm not going to get more. Okay. Nowadays, a typical computer contains millions, billions of transistors. Will a usable quantum computer need millions, billions of quantum gates?
Most likely, yes. And the reason is going to be because of this error correction that I mentioned. What it turns out is that the useful qubits that you can actually use are actually typically far smaller than the number of qubits you might have in the computer. But that is typically the scales that people are thinking about. And then you can go and look through the projections from the various companies and decide if you believe them or not. For example, I think it's IBM are going to double the number of qubits in their quantum computer each year to do it. And so you can do calculations to see when you might expect to get quantum computers of that scale.
And then the last question from Dimitrios. We thank you. Tomorrow, Heather is great, is giving the lecture. Yes, we are very happy to count on her these 3 days. So even on Wednesday, she will be with us. And then, okay, last one. Thank you very much for the lecture. I will be looking forward to the next. It will be nice if the lecture recordings could be uploaded before the next lecture, so that there is a possibility of personal recap. I will try. I will put some pressure in the audiovisual support that they are attending in any case. I will try, but it's not in my hands, okay? So thank you very much for all of you, especially to Heather, but also for all the attendants. Thank you very much.
All right.
See you tomorrow.
Thank you.
Bye.
Thank you very much. Bye-bye.
Bye.